So in this one, we have a differential equation, and for the existence and uniqueness theorem, we want to figure out where this is continuous versus discontinuous. And this already has y prime equals something. So we can say that something is the f function we're talking about, f of t and y. So we want to check where is that continuous versus discontinuous. And can you tell that, does that function have any discontinuities? Are there any discontinuities that arise from a function that looks like this?
If the denominator is 0?
Yeah, we're defining this function as a fraction, so we have to be sure that the denominator is not 0. So we've got discontinuities, discontinuous, if the denominator is 0. And note that this is not just one y value or just one t value. This is a relationship between t and y. So it might be useful to rewrite this by, let's say, isolating y. So if we graph that, we actually get a diagonal line of discontinuities. So on our ty axis, we're going to have the line y equals negative 2/5 t, a diagonal line slope negative 2/5 through the origin. So there's a line of discontinuities. This is one of the boundaries that we'd be talking about. So every point on this line would count as a discontinuity in this function. And we also need to check what else other than just discontinuities in f itself. According to the existence and uniqueness theorem, we need this function f to be continuous. We also need what else to be continuous?
Oh, its derivative to be continuous.
Yes, its derivative, specifically its partial derivative with respect to y. So we're also going to check partial with respect to y, df dy. And for that, since this is defined as a ratio, we're going to use the quotient rule for that. At least that's one way to do it. So quotient rule, we take the derivative of the top. And what's the derivative of the numerator here? If we're looking at derivative with respect to y. Yeah, just -1, because we're treating t as a constant. So the derivative of the numerator times the denominator exactly as is, minus derivative of the denominator, which would be what? What would be the derivative of this denominator with respect to y? Yeah, just 5. Again, we're treating t as a constant, so we just have 5y. Derivative of that is 5 times the numerator exactly as is. And by the way, for the quotient rule, I always have trouble remembering the order. I know it's something minus something, but I can never remember which one is which. What finally helped me remember that is if you look at this in terms of rates of change, if you're looking at a numerator and denominator, and let's say those are both increasing, the numerator increasing causes this to get bigger. So we put the rate of change for the numerator in the positive part. The denominator increasing would make this whole thing get smaller. So we subtract something about the rate of change of the denominator because the denominator getting bigger would make the result get smaller. That's what helped me remember anyway. And then the new denominator is going to be the original 1 squared. Simplifying that a bit, we get -2t minus 5y minus 5t plus 5y all over this whole thing. Looks like the 5y's cancel out. So we get negative 7t over all this. But the important thing is, does that introduce any new discontinuities? Doesn't look like it. It's still the same discontinuities. We still have the same restriction that 2t plus 5y can't equal 0. So no new discontinuities. Our discontinuities are still just everything on this diagonal line. So that's it. That's the boundary here, which means this splits up the ty plane into just two pieces, the half plane above this diagonal and the half plane below this diagonal, which means that any initial value, we would say, given an initial value that's not on this diagonal, we can guarantee that there is a unique solution that goes through that initial value, but we can only guarantee it on that half of the plane. So for instance, if the initial value is, let's say, 1, 1. The point 1, 1, that initial value is on this half of the plane. So that means, given that, we should be able to guarantee that there is a solution and only one solution that passes through that point, but we can't guarantee that it goes past this line. We can only guarantee a solution or a unique solution on this half. Likewise, if our initial value was somewhere below this line, we could guarantee that there's a unique solution, but only guarantee it on the half below the half of the plane below that diagonal. One interesting complication, though, is if the initial value is, let's say the initial value is 0, 0. What would that suggest? What could we conclude from that? Yeah, the problem is that point is on the discontinuity. Since that initial value is on the discontinuity, we can't really guarantee anything. The existence and uniqueness theorem tells you if the initial value is not on a discontinuity, then you can guarantee an existence, that can guarantee that there is a unique solution. Whereas if the point is on the discontinuity, the existence and uniqueness theorem doesn't tell you any information at all. We can't guarantee anything either way. But in general, if the initial value is not on a discontinuity, then you can guarantee that there is a unique solution. And you can even say it should exist in this much space at least. Any other questions on that so far? Or any other questions on just the existence and uniqueness theorem in general? If the point is on a discontinuity, it's not guaranteed. Not guaranteed to be unique and not even guaranteed to exist. Maybe there is no solution. If you have the initial value on the discontinuity, maybe there is no solution. Maybe there is a solution, but there's many solutions going through that point. It's not unique. Or maybe there is a solution and it is unique. We just can't tell any information from the existence and uniqueness theorem. The existence and uniqueness theorem specifically says if the initial value is not on the discontinuity, then we can conclude some stuff. But it doesn't say anything about situations where the initial value is on a discontinuity. So you got to be careful about if-then statements like that. When a theorem is phrased as if A, then B, that means in any situation where you know A is true, you can say that B must be true. But in situations where A is not true, that if-then statement doesn't give you any information at all. If we say if A, then B, that means anytime you know A is true, you can say B must be true. But if you know A is false, that doesn't really tell you anything at all about B. B might or might not be true. You don't know. However, one other useful thing you can conclude from an if-then statement like this is it's what we call the contrapositive. So let's say we know if A is true, then B is true. The contrapositive of that statement would be if not B, then not A. And that will also be a true if-then statement. In any situation where you know that if A is true, then B must be true, you also know the reverse of that. If B is not true, then A must also be not true. One example of this, for instance, might be like if a shape is a triangle, then its angles add up to 180 degrees. That's a true if-then statement. For any shape that's a triangle, we can guarantee that its angles add up to 180 degrees. What would be the contrapositive of that statement?
If it's not a triangle, then its angles do not add up to 180 degrees?
That's not quite the contrapositive, because the contrapositive also involves reversing the order. So if you make all of these not and then reverse the order, what would you get? If
its angles do not add up to 180 degrees, then the shape is not a triangle.
Exactly. If the angles do not add up to 180 degrees, then that shape is not a triangle. That would be the contrapositive, and the contrapositive of a true statement is also a true statement. And that's ultimately because if A then B is saying in any situation where A is true, B has to be true, which means if B is not true, then A couldn't have been true. So if A is false, then B is also false. So the if-then statement doesn't really work in both directions. If A then B does not mean if B then A, but if A then B does mean if B is false, then A is also false. So you can reverse if-then statements if you also apply a not or a this is false to both statements. Any other questions on that so far? Or any other questions on existence and uniqueness theorem in general?
So just to just to repeat, so if a point is on the discontinuity, it's completely possible for there to be like a single solution, but we just can't confirm it.
I think so. It's just that the existence and uniqueness theorem doesn't conclude anything about that point. Because when the if part is true, then the then part has to be true. But when the if part is not true, then nothing is known about the then part, at least not from that theorem. So as an if-then statement, the existence and uniqueness theorem is only talking about situations where the initial value is on a point of continuity. It's not really talking about what happens if the initial condition is on a discontinuity. In those situations, we just can't conclude anything. There might be a solution, there might not. The solution, if it exists, might be unique or it might not be unique. We just don't know from the theorem alone. You'd have to actually try solving the equation and see what you get. Any other questions on that? Or any other topics you want to work on?
Can we also use this y prime equation and find y?
Yeah, let's see if we can actually solve this. And let me also make a note of that discontinuity so we can see what happens if the initial condition is on the discontinuity. So if we do want to solve this, first of all, a good question to ask is categorization. What categories can we say about this? Is it linear versus nonlinear? What order is it? It's definitely nonlinear. And why is that? How can we tell this is nonlinear?
The y term in the denominator?
Yeah, we've got this y term in the denominator. And there's not really any way we can, I mean, we could certainly get rid of that by just multiplying both sides by the denominator. But this would still count as nonlinear because how can you tell in this format that it's nonlinear?
The function that it's multiplied with has a y in it.
Right. It's not just y prime times a function of t or a constant. We have y prime times y itself. Even if we distribute this, we have a y term, we have a y prime term, we have a non-homogeneity, the term without any y in it at all. But this is really the main problem, that we have a term that has y prime and y multiplied together. That's what makes this nonlinear. It's not just y prime times something about t plus y times something about t equals something about t. So this is definitely nonlinear. What order is it? What's the highest? Yeah, the highest derivative that shows up is first derivative. So this is a first order equation. So this is first order nonlinear. If it was linear, we could use the integrating factors technique, because the integrating factors technique is a universal within that category method. The integrating factors technique works anytime you've got a first order linear differential equation. Integrating factors will always work. Since this is nonlinear, we can't use integrating factors. But what other technique might work here? Can we separate the variables here? Is that going to work? I'm not sure if this is really separable either, because the problem is if we try multiplying both sides by the denominator, I'm writing this as dy dt, and then multiply both sides by dt, this doesn't really work either, because it doesn't look like there's any way to get a function of just y dy equals a function of t dt. We've still got a mix of t's and y's on both sides. So it looks like separation of variables also won't work. So integrating factors doesn't work because it's nonlinear. Separation of variables doesn't seem to work because this does not appear to be a separable equation. Are there any other techniques you've learned?
Not that I know of. I don't know.
Yeah, I'm not sure this is really solvable by the techniques in this class. There is one more technique in chapter 2 that works for some very specific first order equations called exact equations, but I don't think this one fits that format anyway. And exact equations are, if you write this as, let's go ahead and put this back as dy dt. Exact equations are if you have an equation of the form some function of t and y times y prime plus some other function of t and y equals 0, which we could certainly write this as if we just subtract t and add y. So we can always write any first order equation in that format. Something times y prime plus something equals 0. Exact equations is if there's a very specific type of relationship between this function and this function. And I don't think that's true here. If I remember correctly, it's something like take the partial of this one with respect to y and the partial of this one with respect to t. If the results match, then this is an exact equation. And there's another technique that can be used to solve that. I don't think that seems to be true here because those partial derivatives are not going to match up. So it looks like none of the methods from chapter 2 are going to work here. I don't think this one can really be solved using methods we're going to see in 22B. It presumably has a solution based on the existence and uniqueness theorem, but that doesn't mean that it's a solution we can find using useful techniques. So I don't think this is really analytically solvable, at least not by any methods we're going to see in this class. Yeah.
Oh, because in one of the daily homeworks, I think for one of the star problems, the function looked like y minus 4x over x minus y, and then like for the different parts. In A, he said to write the function as a ratio of y over x, but I'm not sure how to do that. Like, can we do that with
substitution?
Huh?
Using a substitution sort of approach, maybe? Because in some cases, a problem that doesn't really look solvable can sometimes be turned into a solvable problem by using a certain substitution. But the substitution to use is rarely obvious. It's usually some weird substitution that you probably would never have thought of. But when you make that substitution, everything fits together into a solvable equation. What was the equation you were talking about there?
It was y minus 4x over x minus y.
Then let's try that one.
Yeah, and for part A, it says to write the function as a ratio of y over x.
Okay. Then what might be useful there, if we wanted to write everything in terms of y over x, it might help to multiply the numerator and the denominator by 1 over x. Because that way, all the y's are going to turn into y over x, which is what part A says we want. And any term with an x, the x's are just going to cancel out. And since we're multiplying the numerator and denominator by the same thing, we're not actually changing anything. So dy over dx would equal y times 1 over x. That's just y over x minus 4, because the x's cancel out, over x is just 1 minus y over x. And my guess is if we now introduce a substitution, let's say let u equal y over x, then we get just u minus 4 over 1 minus u. And that, I think, would end up being a lot easier to deal with. The problem, of course, is we also have this dy over dx, which we can't really reconcile with these functions of u. So instead, we're going to have to continue that change of variables and figure out how this new variable u would relate to y and x. Any questions on the substitution so far? So we divided the numerator and denominator by x. We get all this stuff with y over x involved. We make a substitution, just making up a new variable u equals y over x. And I think what we can do there is we can now take a look at how that relates to the derivative. Specifically, let's solve this for y. If we're defining u as y over x, what would y equal?
U times?
Yeah, y would equal u times x. So another way to look at this is everywhere you see y in the original, you could replace with u times x, and then divide both sides by x. You just still end up with u minus 4 over 1 minus u. But the important thing about this is not so much the value of y in terms of u and x, but the value of the derivative. If we take the derivative here, dy dx, how would you take the derivative of u times x?
It would just be u.
It's not just u though, because remember, u is not a constant. U itself is a function of x. So if you've got a function times a function, how would you deal with that derivative?
That would be product rule.
Right, we got to use product rule. So the first part, we could say u times the derivative of x, which is 1. So that first term is going to be u times 1. But then we're also going to have derivative of the first part times the second part exactly as it is. So this means because of the product rule, dy dx can be replaced with this whole thing, u plus du dx times x. So that would be our new differential equation, written in terms of this new variable u instead of the original function y. And is that going to help? First of all, is there any way we could get rid of this plus u?
Or do we just subtract it on both sides?
Yeah, one thing we could do here is subtract u from both sides. So we get du dx times x equals all this minus u. And we'll probably want to combine that into one fraction, which means we'd have to change u into something over 1 minus u. And we could do that just by multiplying the numerator and denominator by 1 minus u. So what would this actually turn into? If we multiply u by 1 minus u over 1 minus u, what's the new denominator, the new numerator?
One minus u squared.
Yeah. So we've got 1 times u times u. So we're really subtracting u minus u squared over 1 minus u. And now we can combine these fractions. So we've got u, it looks like the u's are going to cancel out. We've got u minus u. We've got a negative 4 minus u squared. So we will have that u squared minus 4. And I think that should work. So we get du over dx times x equals u squared minus 4 over 1 minus u. Any questions on that so far? And now we have du over dx times x equals a bunch of stuff about just u. Any thoughts on how we could proceed from there?
Sub back the y over x.
The thing is that we haven't solved the equation yet. If we substitute back in the value of u at this point, we're ultimately just going to get back to where we started. The idea is we're making this substitution ideally to make this easier to make this into a differential equation we can solve. So ideally, we want to solve this differential equation and get u equals something, and then make the substitution back in. So is there any way we could solve this differential equation in terms of u as it is right now? Yeah, this time it looks like it's now separable. In fact, I think the whole point of this weird substitution is to take this non-separable differential equation and turn it into a separable differential equation in terms of a different variable. Because if we now start splitting this up, for one thing, we could multiply both sides by dx. Of course, now we've got this mismatch of a function of x times du and a function of u times dx. But we can reverse that. We can just divide both sides by x and also multiply both sides by this entire reciprocal. So multiply both sides by 1 over u over, or sorry, 1 minus u over u squared minus 4. And also multiply both sides by 1 over x. And at that point, we've now truly separated the variables. We've got a function of u times du equals a function of x times dx. And at that point, with the variables separated, what can we now do?
Plug it back in?
Not yet. We still need to solve the differential equation. But what can you now apply to both sides? Yeah, if we now apply an integral sign to both sides, now we just need to integrate or antiderivative this function of u with respect to u and integrate this function of x with respect to x. And once we've done that integral, then we can substitute y over x for u and solve for y. Integration by parts, in this case, the problem here is not, integration by parts is basically the reverse of the product rule. So integration by parts is what I would do if there was a function times a function. In this case, though, it looks more like a reciprocal or a ratio here. So we've got a fraction. In that case, I would probably try out partial fraction separation. Because the denominator, you can factor that denominator into what times what?
U plus 2 times U minus 2.
Yeah, that factors into U plus 2 times U minus 2. And tragically, nothing cancels out there, which means we are going to need to do integration by parts. But we could split that up ideally into something over U plus 2 plus something over U minus 2, partial fraction decomposition. So if we can split that up, then each one of those individually can be integrated. And the right side, integral of 1 over x, that's just going to be natural logarithm. So we should be able to split this up into partial fractions, integrate each one of those individually. And once we've finished all the integrals, then we can make this substitution again, replace every u with y over x. So this should be possible. Any questions on that approach so far?
After we plug u back in, is that when we try to isolate y?
Ideally, yes. I'm guessing that that's probably not going to be algebraically possible in this case, because I'm expecting this is going to lead to a bunch of weird logarithms. The thing is, I think everything's going to be logarithms. I'm guessing this is going to turn into a logarithm of something about u plus logarithm of something else about u equals logarithm of x plus c. So at that point, if everything's logarithms, I would just raise e to the power of both sides and use rules of logarithms and rules of exponents to split everything up again, or combine things as needed. Let's try out that partial fraction decomposition though. And by the way, I think the same approach would probably work here. If you start the same way, just divide the numerator by t and divide the denominator by t, you're going to get a constant minus y over t and a constant plus 5y over t. So I think the same approach would still work on that one, making the same sort of substitution. But let's get at this, yeah, go ahead.
Oh, how do you know if you divide by x or y, I guess? Or like for the t and y, how do you know if you have to divide by t or divide by y?
To be honest, I'm not entirely sure if there is a universal method for knowing what substitution to make. I think in most cases that you would see in 22B, I would guess that if you needed to make a substitution, the problem would suggest what substitution to make. But I think what these have in common is that they're both just linear combinations of x and y, or in this case, t and y. It's just some constant times y plus some constant times x, or the numerator and denominator are just some constant times t plus some constant times y. So I would suspect that anytime you have something of that format, as long as the numerator and denominator are just a constant times t plus a constant times y, then this approach should work. Divide the numerator and denominator by the independent variable, x or t or whatever, and then this substitution should lead to the same sort of process, same sort of results. Any other questions on that approach so far? And of course, this is just one category of examples of a much broader idea of making substitutions to turn a differential equation that isn't in a certain category into a similar differential equation that is in a category. And once you've made it into a certain category, you can use any technique that works for that category. Like for instance, maybe you have a differential equation that is nonlinear, but a certain clever substitution can turn it into a linear differential equation in terms of a different variable. You could then use integrating factors to solve the linear equation. And then once you've got the solution, reverse the substitution to get back to the original coordinate system. Because that's really all this is. All this change of variable stuff is basically just rewriting the problem in a different coordinate system, or you might even say in a different language. So you take a problem in a language you don't know how to deal with, translate it into a language that you do know how to deal with, solve it in that new language, and then translate the answer back into the original language, the original coordinate system. Let's try setting up this partial fraction decomposition though, because partial fraction decomposition is also going to show up later in the quarter, and I think it'll be good to get a little bit of review. We have this fraction, 1 minus u over u plus 2 times u minus 2. ideally, we want to split that up into two simpler fractions added together. Because this is a complicated fraction. This doesn't show up on a typical table of integrals. There's no substitution that's going to make it easy to deal with. Instead, we want to split it into something over just this first part plus something else over just this part. So this is the idea of decomposition. Decomposition in the sense of splitting it up into simpler pieces. To do that, though, we're going to need to we're going to need to find values of A and B. So how would we start finding values of A and B here? What would be a good next step to do?
Would it be to multiply both sides by the u plus 2 and u minus 2?
Yeah, ideally we want to get rid of the denominators so we don't have to worry about these division by unknown variables anymore. So we're going to just multiply by u plus 2 times u minus 2 to both sides, the whole thing. On the left side, the numerator and denominator just cancel out entirely, so we're left with just 1 minus u. Whereas on the right side, we're taking the a over u plus 2, multiplying by this, and the u plus 2's cancel out. So we're left with just a times just the u minus 2. Then for the second term, we're multiplying, the u minus 2's cancel out. We're left with just b times u plus 2. And now we want to find the values of a and b. And there are a few different ways to proceed here. One way to proceed is by substitution, or not so much substitution, just filling in values for u. Because the idea is we want a and b values that make this true for every u value, which means we can plug in any u value we want. What would be a u value we could plug in that would make this simplify drastically? Yeah, we could plug in 2 for u. We could say, let u equal 2. Just replace every u with 2. 1 minus 2 is -1. And this is going to be especially useful because when we plug in 2 for u here, what happens to this term?
Becomes 0.
Yeah, that whole thing becomes 0 because you get a times 0. So the entire a term drops out, leaving us with only one unknown. B times 2 plus 2. So we can immediately solve for b. So we now know the value of b. Now, if we wanted to find the value of a, what other value could we plug in for u? What would make this term cancel out? Yeah, we could plug in -2. Plug in -2 for u, 1 minus -2 would be 3. A times -2 minus 2 would be -4a. And then b times -2 plus 2 would be 0. So that term drops out. And we can immediately solve for a. So we now have values of a and b. We know a has to be -3/4, b has to be -1/4. And so that means instead of integrating this complicated mess, we'd be integrating this and integrating this separately because integrals can split up over addition. And integrating something over a constant over u plus a constant is easy to do with substitution. It just becomes a natural logarithm. One other approach we could use instead of this is by turning this into a system of equations. So you could make substitutions. We know, let me fill in the values of a and b now that we know them. We know that b is -1/4, a is -3/4. But an alternative method that sometimes works better and sometimes works worse, it really depends on the situation and your personal preferences. But another way to do this is to distribute the a and the b. So we get a times u minus 2a plus b times u plus 2b. And then group these together based on how much u they contain. So you might have a constant term, a u term, and maybe a u squared term, a u cubed term. In this case, we just got u to the first power. But if you group those together, we've got a plus b times u. And then the other terms, the constants, are negative 2a plus 2b equals, and on this side, we've got 1 minus u. On the right side, the coefficient of u is a plus b. What's the coefficient of u on the left side? Yeah, we've got a negative 1 u versus an a plus b times u. So that means a plus b has to equal negative 1. The coefficients have to match up or this doesn't work. So we know a plus b must equal negative 1. And also the constants must match up as well. This negative 2a plus 2b has to match this positive 1. Negative 2a plus 2b must equal 1. And that gives us a system of equations. So you can solve this system of equations using any method of solving systems of equations from high school algebra or Math 22A. And that'll allow you to find values of a and b, which should also be negative 3/4 and negative 1/4. So both of those methods will work. There are some situations in more complicated cases where one of those methods works better than the other one, but it's really, for most cases, just a matter of personal preference. It's good to be familiar with both methods because, as I said, sometimes one of them works better than the other, but either one should work. Then you integrate those. This is just going to turn into negative 3/4 times natural log of u plus 2 when you integrate, because the denominator is just a linear function. It's just 1u plus something. And then this one, with just 1u plus something or minus something, it's just going to be a natural logarithm. So that's this entire integral becomes just this. We get that integral, negative 3/4 logarithm of u plus 2 minus 1/4 logarithm of u minus 2. And then what's integral of 1 over x? Yeah, that's just logarithm of x. And because we want all solutions, we'll also include plus a constant. And at this point, I would also, I think I would raise e to the power of both sides here, because ideally we'd like to get rid of the logarithms. You could also move these multipliers in as exponents. So we've got e to the logarithm of u plus 2 to the negative 3/4 times, because we're combining the addition inside the exponent because of multiplication. Addition combining the logarithms because of multiplication. U plus or u minus 2 to the negative 1/4 equals, and likewise here we could split this up, e to the logarithm of x times e to the c is just some other constant. And at that point, the exponents and logarithms cancel out. So we get u plus 2 to the negative 3/4 times u minus 2 to the negative 1/4 equals x times some constant. Probably be a good idea at this point to multiply or to raise both sides to the power of 4 to get rid of the fractional exponents, then replace every u with y over x. And at that point, maybe you can solve for y, maybe not. But either way, you've at least got a solution relating y and x in implicit form, even if you can't explicitly solve for y. Any other questions on that? All right, then that's it for today. Feel free to email me if you have any other questions or if you want to request any examples for next time, and I will see you then.